Okay, good afternoon. I am Nikos. I'm a data scientist at GRNet at EuroCC Greece. And I will present a notebook named the GPU Accelerated Linear Algebra in Python. We will see some basic linear, a bit more high level than previously, in the sense that we will use the functions of QPy, which allows us to achieve all the cubeless functionality with the corresponding functions. I will share the notebook link in the chat now. The chat is here. And I suggest that I prefer to do this as an interactive session. So I suggest that you open the link, you make a copy on your drive, and then change the runtime. If it is not, you go here runtime, change the runtime type, and you select a GPU, any GPU. I have the paid version of Colab, so perhaps you will view less options here, but you should view something similar. Please let me know if you have any issues of opening the Colab notebook. Okay, I hope everything is fine, so I will continue, but feel free to interrupt me and ask any questions. At the top right edge here, you can view the resources. Here we have a RAM of 12 gigabytes, a small GPU of 15 gigabytes, and the hard disk. If we run now the first cell, this is the equivalent with NVIDIA SMI for HPC. The link again, yes. I share it here. This is the equivalent NVIDIA SMI command. And we can view some basic information about the GPU, which GPU we are using. Here we use a Tesla T4, the energy consumption, and the GPU RAM. It has 15 gigabytes of RAM, etc. Basically, this is an indication that everything is okay when we start. So we continue with importing the NumPy, importing the operating system. This is just to view the number of processors. This is important because we will compare NumPy with QPy. And it is important to know at this point that the comparison regards this number of processors, only 2 processors. So in systems with more processors, even on our laptop, most probably the comparison will not be so, the differences will not be so big. But okay, definitely you can run this notebook locally. You can download the notebook and run it locally, or on an HPC facility, the same. So we have 2 processors, and here we import in QPy, and we print some basic information. We can view the total GPU memory and the free GPU memory here. Let me ask if everything is okay till now, if you want to ask me something, if you are able to run the notebook, the link is working, etc. I hope everything is fine. So we start our operations with some simple matrix multiplications. We initiate a matrix A and a matrix B. We give with a parameter n, a parametric matrix, and we do matrix multiplication, and in order to benchmark the compute time, we do this 10 times. We repeat the same process 10 times, and we just count the time for each iteration, and we average the results. So I run this now. I give the input n, which is 1000. So we have 1000 by 1000 matrix. And I run the first block. So I can view that the NumPy time is 0.03 seconds. I run the second with QPy. Sometimes on the first run, perhaps the time will be more when you run CUDA. So perhaps you need to run this again. But okay, we can view that the QPy time is much less. It is like if we divide the NumPy over the QPy time, we get a ratio of 43. And this is for n 1000. Let's go 2 steps before here, where we defined n, and we change this to 2000. And again, we talk about the smaller matrices. For bigger matrices, it will be even bigger. Now, if I run NumPy, I get 0.28 seconds on average. I run QPy, I get this time number here. And if I divide the 2 times, I get a ratio now of 300. So if I have a big matrix and I want one day to do matrix multiplication with NumPy, with QPy, one day with QPy, then with NumPy, I would need 1 year. This is a huge difference. But again, with the limitations of the current system, okay, this is important. Inside the notebook, I have some notes together with the code. So here I write that QPy is optimized. Okay, actually it is calling QPlus. I say again, if we had multiple threads, the ratio would be smaller. And GPUs have, one of the reasons that we have this difference is that the GPUs have higher memory bandwidth compared to CPUs. Let's continue with another simple operation, which is the element-wise addition. And then we will continue with a solver. We will build our own linear solver with some very, very basic linear algebra calculations. And then we will train a neural network, again with similar baseline calculations in very simple steps. So we have element-wise addition. Now, because this is a vector, I have a bigger number here of 100 million elements. So I give n. And similarly, we have a for loop for the addition of the vectors in NumPy and the vectors in QPy. With underscore NP is the NumPy vectors and the CP is the QPy.
Why do we need the line with GPU initialization warm up to ensure GPU is initialized?
Which line? Which line?
14.
This is because what I said previously, because sometimes when I run as a first time, I call CUDA, it does some compilation, I think, or some operation at this point, and it takes some time. If I call it again, the time will be much less. So in order to benchmark the application here, I put some operation on CUDA, anything, just an addition here, in order to bypass this step, this compilation step.
Perhaps it's a bit of cheating, I think. You should
cheating, no, cheating would be the opposite if I didn't have the line. Why cheating?
Because this takes some time. So computation time of
CUDA, I don't count the time here.
We should.
I count here the time.
Yes, I think we should also count the initialization time.
No, because look, you can do this even with, now I understand, I think, what you say. You can do this with a smaller array, like 10 by 10. You can warm up I can do it here. I think I can do it here.
Because I think that this also preloads the cache memory on the
Something, yes.
So it's you also hide the latency of transferring data to the CUDA graphics card.
No. The data here, the data are transferred. The data here are transferred. Yes. Yes.
Perhaps
We count only the operations. Okay. We can do this actually. We can convert this here. Where am I here? After the time. This is a good point, yes, because we don't count this time. It depends what you want to benchmark, actually. Okay, so, and I also get this here. Otherwise, it will already be.
Okay, this seems a fair comparison now.
Okay, great. So, I think I did everything. It takes some time. I say again that it depends what you want to benchmark, of course. If you want to benchmark just the linear algebra calculations, it was the previous. If you want to benchmark the entire process, it is this. So you have a good point that this should be done. If we want to benchmark the total time, we should do this. Just a moment, I have a comment, I think. QPy versus PyTorch, which is faster? I haven't benchmarked QPy with PyTorch. Actually, I prefer I use the QPy here because it is simpler. It has a simpler interface. It has exactly the same functions like NumPy. But I guess that it will be similar or very close because both call QPy behind the scenes.
Now the NumPy seems better using
now
this.
the NumPy, yes. So you were correct. Yes. Okay. Just a moment. Give me a moment. I will comment on that to share the link. Yes. Now the NumPy time is less than CUDA because it takes some time to transfer the data to GPU, and this is one part of this presentation. We will view this later more clearly because the idea is to send to GPU very big elements, very big batches of data.
Can we also perform in parallel? So asynchronously, we compute on or transfer using some kind of software pipeline on CUDA and also on CPU at the same time? To achieve the maximum speed up. So we start some threads on the CPU, work parallel, at the same time asynchronously send data to the CUDA, and as long as it computes these arrays, we start sending another batch to the graphics card, performing a software pipeline.
This is a good idea. Personally, I don't know how to do this. I should ask ChatGPT and return, but it is a very good idea. I guess that we will need a framework like MPI or something to do this, because if we use Python, executes line by line the code, standard Python. So it will wait the first.
I would suggest with thread pools on OpenMP.
Or thread pools,
on
yes.
Python.
Yes, perhaps, yes. Or thread pools, yes. Great. I am happy that we have comments. So this is, what was your name? Sorry? Okay.
What? Okay,
your
thanks.
name?
I'm Minas.
Minas. Okay, thanks, Minas. Thanks for the suggestions. So what we saw now was that GPU is less than CPU time, and if we make the size of the matrix even smaller, like 1,000 elements, and run again, then we get 100 times slower the GPU. Okay, so this is what I was saying previously. I cannot make this 1 million because I am already around 3 gigabytes, so I will make this 200 and run this again. Probably previously it was 0.6 NumPy around two times faster. Now, if I run this again, let's see the results. Now I send a bigger batch of data to the GPU and it crashed, okay, because it has it doesn't have enough memory. So I will start from scratch. I will import the libraries. And I will do this 10,000 to see gradually the difference. .4, a bit less. So this confirms our rationale. Now, if I convert the code as it was previously, and if I want to benchmark only the calculations time, and to my perception, Minas, I think this is important because if you want to do this, if you have the data on GPU and you want to do more complex calculations, like just rather than just adding the elements, it is important to know also the time there. So I run this again without by initializing the arrays before the for loop of the benchmarking. Now I get 38, a ratio of 38. So we have a bigger time for NumPy. And again, if I do this like 1,000, and I run again, still now NumPy is like 20 times faster than the GPU. Okay, so two conclusions. The first is we need to send big batches of data to the GPU. And the second, it is we need a GPU in order to perform complex calculations. Okay, till now, any other comment or questions?
How we transfer back the results from the graphics card?
To get the results to NumPy again?
Yes, from graphics card to bring them
this
back.
Function cp.asArray.
This transfers to the A array.
For instance, here there is. Okay, let me write code here. I will get this. Here I initialize a NumPy array, then I transfer this to the GPU. And here, if I write cs.array a_cp, I get it back to the CPU. So now this is a NumPy array, the final. Let me do this smaller.
So the third line should be a underscore and p equals CP as array.
Yes, this is why I selected this instead of Python. You have for many functions of NumPy, it is the same, but with CP. It is the same as with
but the target array is missing. Only the source array.
Which is the target?
ACP is the source array, so we copy.
ACP is the QPy.
Oh, the fourth line. Oh, the fourth line.
Yes, here I don't save. I just get it on the fly.
Ah, on the fly, no stored locally.
On the fly, yes. Okay. So what else? Yes. So that was the first part with some basic calculations. And now we will continue with the linear solver part. As I said, we have three parts. The first, the second with the linear solver, and the third with artificial neural networks. Here, we will solve a linear system. We have an input matrix X, and actually the equation is X times A equals Y, and A is unknown. We have X is a matrix, Y is a vector, and we want to solve the system. A are the weights of solving the system. I have the link if you want to view more details on the method. Here it is posted on Arxiv. And basically the algorithm initializes some weights A with 0, computes the errors, which is Y minus X times A, and then it has a nested for loop. The first loop is for some number of iterations N, and the second is where I iterate all the columns of X. J here corresponds to the columns of X. We compute a dot product among X, J, which is the column J of X, and the E, where is the current error, Y minus X times A, over the dot product of Xj with itself, Xj with Xj. And then we update the errors like errors equals errors minus Xj times dA, where dA was the result of the previous calculation with the dot product. And we update also the weights. Aj becomes Aj plus the dA. If we run this iteratively, this converges to the solution. Now, we will run this on CPU and on GPU. This is the serial part of the method. We will view this, the issues with the time, and we will view then the batch part of the method. So here I initiate a matrix with 100,000 rows. Rows is observations, with 1,000 columns. It is the vars, and with 10 iterations. Okay, I will run the algorithm for 10 iterations. So I give the dimensions of the matrix here, and here I initiate the matrix with NumPy, np.random.rand, etc. A random matrix, -1/2, in order to have positive and negative random numbers. We initiate the weights A, which I hide from the algorithm. This is the actual weights, and I compare with the computed here. At the end, I subtract the actual A minus AA, which are the computed weights, and I print the difference of the errors and the NumPy time. Now, the algorithm is here for I in range iterations, and then for J in range variables. This is what we said previously. We take each time one column of x, x of all, comma j, and we divide with the xxj. In order to avoid computing each time the dot product of xj with xj, we compute it here all at once. If we take the summation of x times x, the times in Python is element wise. So if I do element wise multiplication and then summation, this is equivalent to the dot product. So xx is the vector with all the dot products of the columns. Anyway, I hope you understood the basics. It is not very important to understand fully the algorithm now. The idea is that we do the important part is that here we perform a dot product operation. This is time consuming for big matrices. And here another multiplication of a scalar with a vector. And then a subtraction of two vectors, E minus equals this. Okay, so we have these three basic time-consuming calculations, and we do this iteratively. Okay, so I am running this. It takes some time. Now it is running. It is
the error. How it's computed?
The error is the initial weights A. Okay, here I have the correct weights, but I don't give the correct weights to the algorithm. I hide them. And AA is the south weights, the weights I try to find. So I compare the weights that I found with the actual weights. And the difference is in the order of 2 to the minus 2 times 10 to the minus 14, a tiny number. So the algorithm converged. A is this here. It is the expected output of the algorithm. Okay, and I have the NumPy time. I have the NumPy time, which is 13 seconds for this. Fair enough to solve
this algorithm, where it is used in physics?
It is a generic algorithm, a linear solver. I have here the arXiv paper. I have the link here. It is general purpose algorithm to solve linear systems. You can use it in physics, in machine learning, if you want to do, for instance, a linear regression for a very big system. It performs well on tall matrices. When you have a fewer number of columns than rows. And also it performs well in very big matrices. I have some benchmarks here with LAPAC, with BLAST. And you have a speed up of for a matrix of 4 million rows and 10,000 columns, a speed up of 132 when compared with BLAST. BLAST is highly optimized. Okay, you can do this with.
I have another question. How this paper is published on arXiv and not on a journal, perhaps, or a peer-reviewed process?
It is not yet published on journal. It is
work in progress.
It is a work in progress. Yeah, I didn't have time to finalize some. I wanted to finalize some experiments
and aren't you afraid that perhaps somebody from another country stole this and published it? Because it's a bit dangerous to put things somebody can.
Look, basically, when posting on arXiv, it is somehow like a confirmation that you own the idea. Of course, somebody can take small ideas and make an advanced version or an even better version. But okay, Personally, I do not care. I mean, I do this because I like. So yes. Now the archive, posting on archive is something common. Okay, and even journals accept this and pre-post something on archive, and then some journals give you the opportunity to also link your published paper in the journal with archive, to say that the initial version, because if you publish not in open access and somebody wants to read the paper, he can read the archive paper, but the archive is without the peer review. So it is a first, it doesn't have the corrections that the reviewers will find. So I mean, it is like a standard process, especially in disciplines like computer science, physics, engineering. It starts becoming like the norm, as far as I can see. So it is, yes, it is like some standard process. Okay, anyway, this is for publications, but let's continue with the calculations. So this took 13 seconds to run with NumPy. And here with QPy, it is 2 seconds. We can view a reduction. The error is still very low, like 10 to the minus 14. So we confirm that both algorithms work well. And if we divide the time of NumPy and the QPy, we get a scale factor of 4. But this is the first version of the algorithm with the dot products. The dot products, we can see here that it is good to send them to GPU. Okay, again, in order to avoid the cheating, here everything is already in GPU when I count time. But here I don't need, there is no need for the algorithm to transfer many times the GPU. I can transfer them at once, and I can do my operations many times, the iterations then. The data are on the GPU, and I can do as many iterations I want. If I had more data than my GPU can hold, then that would be a problem. And basically, that was part of the first presentation using GPUs with MPI, etc. Now, let's continue with the algorithm. What I do when I run the algorithm with batches. This is the modified version of the algorithm. We can see a third nested loop. Here we have the first for the iterations, the second now, instead of running each one of the columns like I do previously, simply x of all comma j here, I take one column. Here I do this in parallel. So I start for j in 1, comma threads plus 1, comma 2 times threads plus 1. I assume that I have THR threads. THR threads. Okay, so I can do this operation for all the current threads, and then update the weights and subtract the error and follow afterwards the same rationale of the algorithm. This parallel approach, I can do it in a more smart way. I will explain what I mean smart way. Instead of doing this in parallel, like writing a parallel for loop, I can simply compute the dot product, not of x, not of only the j column of x, but of x from j to j plus batch, where batch is the batch size. Here I use 100 columns. And if I take the transpose of this and I multiply with the errors, I have very simply in one operation the total dot products. Like I was doing this in parallel, but behind the scenes, utilizing the plus functionality here behind the dot. The plus functionality to multiply matrices, which is optimized instead of doing this in parallel for each one of the threads, blah, blah, blah. Okay, so this is for theory. Now, in practice, regarding code, here I have, again, one outer loop, one inner loop with batches now, with a step here in the range, and the dot product is with a bigger dot product. It's a matrix vector product. Previously, I had the vector product. This is important because we're going to compare CPU time and GPU time. So here, previously, we compared vector operations. Here we compare vector. Here we compare vector matrix vector operations. Okay, it is running again. NumPy takes approximately the same time as previously. Why? Because I have only two processors. The error is a bit higher. Okay, again, it is 10 to the minus 13, but it is 10 times bigger like previously. Why? Because this is an approximation of the algorithm. It is not the pure version of the algorithm. However, because we update the errors and the weights, actually the initial algorithm is weights to update the errors, to update the weights, and to compute again the delta alpha, the difference of the weights. Now, for the batches, we do for all the batches this at once. So we skip some, we have some accuracy reduction. But okay, it is acceptable for this problem. Now, so I solved this with NumPy over here. I solved this with NumPy, and I solve the same now with QPy. Again, I initiate a random matrix. I run this. Now I can view that the NumPy over QPy time is 23. Previously, with a serial vector of version of the algorithm was 4. So we view again an improvement. We view a clear improvement. Why? Because we send the data are already in the GPU. We say to the GPU to compute something in batches, to compute something bigger each time, and not smaller many times. And this is much more, we can view here that this is much more efficient. If I had a bigger GPU, I could increase the sizes. And for instance, if I decrease the size here and I run for 1,000 observations, what do we expect? Not 1,000, make this, what was previously 10,000. I have an NumPy time of 0.8, a QPy time this. Okay, again, it is 20. It is a bit less than previously. If I make this even smaller, 1,000 with 100, with 100, now NumPy is faster. You see, the same as previously. Okay. Any questions till now? No. And okay, we are at the end of the time. I will very briefly present another method, just to view another functionality of QPy for the comparison of the least squares with NumPy and QPy. Here, this is a method for training artificial neural networks. It is published here. You can view the paper. Actually, the idea is that we split our data into clusters, into very small clusters of data, and each one of these clusters correspond to a neuron. We solve there locally for the data of this neuron / cluster. We solve a linear system, and we can compute the weights of this neuron. We do this iteratively, and we have very, very fast all the weights of all neurons. And then I simply solve for the external layer, again, a linear system, and I compute the weights for the external layer. Okay, I have the details here. It is not so important. It is important from a code perspective, I mean, to view two operations. I will tell you now. Here I will train a neural network with 1,000 neurons for a problem with 100,000 samples and 10 variables. So it is a big dataset with few features, 10, but a lot of samples, and a lot of neurons also, 1,000 neurons. So this is the problem. I initialize some variables here. I compute the number of the observations for the internal neurons. Here I transform my initial vector of target variable y. I forgot to say that I have x and y, which is the training set, and xt and yt, which is the testing set. Okay, and I run the first part, which is the computation of the internal neurons. Here, I get a NumPy time of 1.8 seconds. The basic operation is here. The time-consuming operation is here. Here we use the linear algebra least squares function of NumPy for small systems. Okay, these are small systems of 100 by 10, something like this. Not exactly like this. But I do this 1,000 times. Okay, and I get NumPy time of 1.8. I run this again. Okay, this is very fast, 1.9. Then I compute these weights with my initial matrix X, and I put them in the sigmoid function, tan H. And here is the second part, I said previously, that I solve now for the external layer. I have to solve a system X times V equals Y. X is 100,000 times 1,000. 1,000 is the number of neurons. Now, instead of calling least squares, and in order to benchmark another method, we call the method solve here. The solve is the solver for square matrices. Now, in order to transform this to a square matrix, I multiply the transpose of X with, of layer 1, X hat is layer 1, of X hat times X, and I solve for X hat transpose times Y. I solve this. Okay, so instead of solving, 100,000 times 1,000, I have a matrix multiplication first, which needs some time, and then a solution of a 1,000 by 1,000. This is a trick we do in solving equations if we know that the rank of the system, the system is full Calon rank. Otherwise, this will not work. Anyway, I have a NumPy time of 7. I check the accuracy here in the something happened here, 0.8. I changed something. 0.8. Anyway, previously it was 1. Here I can see some noise. I don't know why. No, something has happened. I think I will run this again. This is very fast. Perhaps it confused some variables I ran previously. Because I ran this cell twice. Yes. I ran the inner cell twice, I think, because of that. Yes. Now we have an accuracy of 99.9% in the test set. Okay. So the algorithm works. And we do the same with CUDA, with QPy. Now we transfer the data to the GPU. We assume that we have enough GPU RAM. We initialize the variables. We compute. It is exactly the same code. You see, cp.linarg.lstsq instead of np, etc. Now, this with the small matrices, perhaps you already observed that it is slower in the GPU, although the data are already on the GPU. Here I formulate the external layers, and here that I have the matrix multiplication and solution of a square linear system, the time is again less. I check the accuracy to see that everything worked well, and I see a 99% accuracy again. And I compare now the time in the inner layer with the small matrices where NumPy is faster, 10 times faster, and the time for the outer layer where QPy is faster. Yes, it is 2 times faster. Okay, this depends again on the size of the matrix, etc. So somewhere here we finish some conclusions. We discussed about matrix multiplication performance and element-wise operations. We see that for larger arrays, CUDA is faster, but again, we have some overheads when sending data to the GPU, and this is important to take them into consideration as well. That's why we prefer to send big data to the GPU. QPy handles larger batches more efficiently, as we saw in many examples. And of course, if we have larger data sizes, we will need other frameworks like MPI to parallelize across many GPUs. That's all from my side. We can, of course, discuss if you have any questions or ideas. Please feel free to ask.